तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody and welcome back to the lecture on computer graphics. In the last couple of lectures we have been discussing about display devices, specifically about CRT monitors, okay? And I said earlier that there were three types of CRT monitors: the DVST, the random scan and the raster or the raster refresh raster scan. We have discussed about raster refresh quite at length, and we continue in this lecture also. And if you recollect what we have been doing in the last class, specifically to do with the refresh raster scan, it is different from the random scan or the DVST in the sense that those were line drawing, stroke or command lines, and in this case it was point drawing. Okay, so we came to know how to draw points on the screen. We had also seen the architecture of a typical raster graphic system in terms of video controller, display processor, frame buffer, monitor and things like that. Of course, in addition to the keyboard, mouse, CPU and the system bus which a typical computer system will have. We had seen the internals of a video controller which takes in the input from the frame buffer in terms of the intensities of the pixel, and it keeps on generating the horizontal and vertical deflection voltages for the horizontal and vertical deflection plates to make the beam move from right to left, down, below and also go back. We will talk about the retrace later on today. And at each point it must know what is the intensity of each pixel. Based on that it must control the intensity of the beam which is firing the spot on the screen. So we have seen the internals of a video controller. We had also seen the mechanisms of drawing points as well as lines. Remember, a line, a curved line or a straight line is also drawn on the screen in the case of a refresh or a raster scan by basically joining or drawing a set of points, and this gives rise to the effect of what is called the staircasing, jaggies or aliasing effect of a line. Okay, in general we have that effect, except for very special cases of a line we will typically have the effect of aliasing of a line. So we had seen that. We have also seen the memory size requirement in terms of the frame buffer memory required by the video controller or display processor, and we had seen the increasing size requirement of the frame buffer as the value of n, that is the number of bits assigned for a single pixel or a point on the screen. If n is equal to 1, we call it as a bit plane and we have a pure black and white image, whereas in the case of when n is increased from 1 to 3 to 8, let us say, we typically start having different colors or gray shades or a combination of both, and also n can be raised to as high as about 16, 24 or even 32. Resolutions were considered about 512 by 512, 1024 by 1024, but you can go beyond that, 1280 come 1024 or even 1700 cross 1800. Very high resolution monitors are also available which will require frame buffer sizes of in the order of several megabytes. Okay, if you look back into the last screen which we visited in the last slide, we were talking about concepts of refresh rate, video basics and scan conversion. Just to keep the continuity, I will go through this slide once again. We talked about the refresh rate of a CRT as given in the first line here. Our refresh rate of a CRT is the number of times the image is drawn on the screen per second, and we had seen that the minimum recommended rate is 30 hertz per second, but you should provide about 60 hertz per second or if possible more for a flicker free display. That means the user does not feel any iteration of the picture which is flickering on the screen, because we know that the next line says that the reducing the refresh rate increases the flicker in the screen. Okay, so that's very natural. And the third line states that the horizontal scan rate, that's a term we are coining here, is the number of scan lines the circuit, that means the video controller basically, it drives a CRT display per second, and it is basically the refresh rate multiplied by the number of horizontal scan lines or scan lines. Okay. The important part in the lower part of this frame, as you see here, is the resolution. It's very important. What do you mean by the resolution? Resolution of the screen doesn't depend upon the system you are using, the graphical card or the computer graphic system. It entirely depends on the monitor or the screen which you are using, and which in turn depends on this physical dimension of the very small spot size on the screen. As we go along, we will see about what do you mean by spot size or the pixel size on the screen. We will see figures on that soon, but the resolution of the screen depends on the spot size. This CRT resolution is not a function of the bitmap resolution which the programmer can set. So he has to find out what is the maximum resolution a screen can support, and corresponding to that he has to set the resolution of the frame buffer and draw his picture accordingly. He can never in fact draw a larger resolution picture on a smaller resolution screen. Well, the software can handle such effect of zooming effects, which we will see later on, but typically if you try to draw 1024 points on a screen which has only 640 by 480 points in the horizontal and vertical directions respectively, you will never be able to do so. So you must know the resolution the system supports and gives you what is the maximum resolution it can support. And if you want to have larger spot size on the screen, automatically the resolution comes down. That means typically high resolution monitors have very small spot sizes, but it is of a finite small dimension. Okay, and the last point is the horizontal resolution also depends on the spot size as well as the beam switching speed. This is a new term which we will see today. What do we mean by beam switching? That means the rate at which the beam should be turned on and off. We know why the beam has to be turned on and off. You remember the previous figure in the previous slide, as the beam was taken from the left of the screen to the right of the screen, you had to put points on the screen. Okay, so depending on the number of points which you have to draw on the screen for a horizontal scan line, the beam has to be turned on that many times depending upon the number of points which you have on the screen, and of course you have to switch it off that many times as well. Okay, so you have to switch on the beam as well as switch it off depending upon the number of points you have on a horizontal scan line. Okay, and let us talk more about that in the next slide as we continue discussion on the refresh rate, video basics and scan conversion. We talk of the bandwidth of a display. Typically the bandwidth terminology comes from signal processing theory. It typically talks of a range of frequencies which the system can support, or you can visualize it to be the maximum frequency which the system can support. We are talking of a frequency, that means the rate automatically comes somewhere, and the bandwidth of the display is defined in this case at the rate at which the beam can be turned off to on and vice versa. I repeat, the rate at which the beam can be turned off to on and vice versa means of course on to off, depending upon, this depends on the number of points you actually have on an individual scan line. Okay, let's take an example. If you have n pixels per scan line, that is dictated by the resolution of the screen, the n could be 512 or 640 or 1024 or even 1280. Okay, these are the typical values, let us say, for standard monitors per scan line. That you have, let us say, n pixels per scan line. It is necessary at the maximum to turn the electron gun at a maximum rate of, I am talking of the word maximum because it has to do with the maximum rate or the bandwidth of the display. So we are talking of the maximum rate at which the electron gun has to be switched on and off. In the worst possible case, it had to be turned on n by 2 times, half of the resolution of the scan line, n pixels. So if you want alternate pixels to be on and off for n pixels per scan line, you have to turn on the beam n by 2 times. That means if there are 512 pixels or points on the screen, you might have to do it 256 times on and 256 times off to cover alternate 512 pixels, where alternate line points will be white and alternate points will be black. And if you keep doing it for all horizontal scan lines, what this will create, you can almost imagine that the first pixel is white, the second pixel is black, the next pixel is white, white, black, so on. Alternately this goes on. For each scan line, if the same pattern is repeated, you typically have a texture pattern which is called, I will say that you will start to visualize alternate vertical black and white lines on the screen. So as said here, if you turn on the beam n by 2 times off, n by 2 times on, this will create alternate black and white lines on the screen, and it is at this situation you have the maximum rate at which the beam has to be turned off or on. Okay, so that is that could be defined as the bandwidth of the display. Okay. Let us now look at some other concepts of video basics and scan conversion which are necessary for calculation of this bandwidth, and also it is related to the memory size, because memory size is dictated by the value of n. Okay, this is a typical example of a raster scan, highly simplified, but just to illustrate you what the raster scan mechanism means. Okay, the blue lines, blue horizontal continuous lines are the scan lines. So just one example given here on the board, on the screen, where there are about 1, 2, 3, 4, 5, 6, 7, 8, 9. So I take a very simple example just to show 9 horizontal scan line as continuous blue lines. Those are the horizontal lines over which the beam will move. And once it starts, let us take the first line. As it starts from the top left corner, it scans and reaches the top right. The beam has to go back. The beam has to go back and start to scan once again from left to right. Again it goes back from right to left, and again it goes to the right. As you can see, as we are doing this for one cycle going forward and back, there is a little bit of incremental displacement which keeps happening in the vertical direction. In some cases you will also find that the horizontal scan, when you move from left to right in the screen, okay, I say left to right in the screen, as you are moving, that is also inclined. But if that is not inclined, definitely the red dashed line, discontinuous dashed line which you see which is marked as horizontal retrace. This line, the horizontal retrace scan path which takes the beam from the right hand corner to the left hand corner, is called the horizontal retrace. So that means you have a horizontal scan line, then a horizontal retrace back, again a horizontal scan line, and again a horizontal retrace back. So these goes on for n such horizontal lines. In this figure, a very simple example we have taken where n is 9, but it typically should be a few hundred to 1,000 or more. So this keeps going on for n number of lines, till at the end of the last cycle what will happen is you will reach the bottommost part of the screen. Somewhere here on the bottommost part of the screen is where you will reach, that is the horizontal scan line will take you there. You can't go on. Again, you don't need a horizontal retrace here because there is no line beyond the last blue line or the last horizontal scan line. So you basically need to go back. Why do you need to go back? Remember refresh rate, remember refreshing, which is necessary for flicker free display and which is necessary for the persistence of the phosphor. This short persistence of the phosphor demands that you keep visiting the pixel at a very fast rate, typically 30 to 60 hertz. So you need a mechanism by which the beam will now go back from the bottom right to the top left of the screen, and this path, which is shown by a slightly pinkish dashed line, discontinuous line, is called the vertical retrace. So that is called the vertical retrace. The vertical retrace takes the beam from your bottom right of the screen to the top left. As you are watching this picture, your bottom right will be here, top left will be here. You keep on scanning, horizontal scan, horizontal retrace, horizontal scan, horizontal retrace, horizontal scan, horizontal retrace. We will see an animation of this very soon with a simplified picture, not with this slide. But as you are finished with the last horizontal scan at the bottom of the picture or the bottom of the screen, you don't need to make the beam do a horizontal retrace anymore, because that's unnecessary. You don't need to do that because there's no line visible beyond this last horizontal line. You need to basically refresh. To do the refresh from the bottom right of your screen, you need to take the beam back to the top right, and that is called diagonally the vertical retrace. So horizontal scan, horizontal lit trace, horizontal scan, horizontal lit trace, and so on. At the end of the last line, bottom right, you need a vertical lit trace. So you can now imagine the horizontal and vertical deflection plate voltages, or voltages to be applied to the horizontal and vertical deflection plates, which will make the beam move very fast, horizontally retrace, horizontal retrace, and so on. And at the end, you need both voltages to change in a linear manner such that the beam moves from the bottom right to the top left. So that both the deflection plate voltages must be active to do that. When you are just doing a pure horizontal scan, maybe the horizontal deflection voltages are important. You don't need a vertical deflection voltage to change in this direction. The beam is only traversing in the horizontal direction, so horizontal deflection voltages at the horizontal deflection plates, which is essentially vertical, we talked of this earlier, is important, which makes the beam move. Then again, this is important when it retraces it back, and at that retrace, since there is an incremental movement in the vertical direction, the vertical deflection plates also have a role to play at that point of time. It is switched off on, and at the end, when you move for the entire vertical retrace, both plates must play a role to make the beam move very fast from top down to bottom up on the screen. Okay, so coming back to this picture, that's the mechanism of this raster scan. We have horizontal scan, blue lines. I repeat again, horizontal trace, dashed red lines, discontinuous one, and a vertical trace diagonally across, which is given by the dashed line. Also, the arrows, the vertical trace shows in the path in which it is moving. Okay. Well, continuing with this picture, let's take some basic video standards. Typically, there are two video standards, NTSC and PAL. The NTSC is the American standard and PAL is the European standard. In Indians, we typically have the PAL standard video, but I have just taken an example from the NTSC, which is the American standard video, which has 525 horizontal scan lines with a frame rate of about 30 frames per second. That is prescribed for video. In terms of TV transmission, monitors will definitely have a larger frame rate, and the viewing aspect ratio is 4:3. So you can imagine the number of scan lines and the number of points per pixel per scan line will be different, because the aspect ratio is not 1:1 but 4:3. Each frame, this is interesting and different. The first time we are introducing a concept of what are called the fields. Each frame has two fields which cover half of the picture. Now, this half of the picture doesn't mean that you cover only the first half and then the bottom half. These frames or these fields within each frame, there are two fields in each frame. These fields are interlaced. We will see that. Okay. So these fields are interlaced or interwoven, and we will see a picture. What do you mean by this interlacing or interwoven of fields? Each field is consisting of half the picture, means half the number of total scan lines in each frame. Okay. Fields are presented alternately every 1/60th of a second. Since if you talk about 30 frames per second, that means you're talking of 30 hertz, each frame being presented 30 times per second, and each frame consists of two fields, not successively. Let us assume there are two fields, field A and field B, and both these frames must be present in one frame, or they must be presented or scanned for each frame. So if you are doing the frame 30 times per second and there are two fields, 30 into 2 gives you 60 fields per second. That means each field must be presented on the screen at the rate of 60 times per second, or the field is basically scanned at 1/60th of a second. So that's the way. In fact, the sentence should read: the fields are presented alternately every other 1/60th of a second. So that's the correct way of talking about it. So 1/60th of a second one field, 1/60th of a second second field, and so on. This will go 60 times when you cover the field that we had covered basically 30 times each the frame. Okay. One field contains odd scan lines. If I number the scan lines, horizontal scan lines, in terms of starting from say 0, 1, 2, 3 in digital world, or 1, 2, 3, 4 in whatever way, I say odd scan lines 1, 3, 5, 7 and so on are the odd scan lines corresponding to one field. And second, we have the other field which contains the even scan lines. You can start from 0. I have taken the numbering from 1, but you can always say 0, 2, 4, 6, 8. Strictly 0 is neither an even or odd, but if you have the numbering starting from 0, you can take that to be a part of the even scan field, 0, 2, 4, 6, 8 and so on. So that's the even field. Okay, we have the odd field with odd numbering scan lines and the even field with even scan lines. Now you can see what they mean by the fields are interlaced or woven. So when you are covering one field, You don't cover two fields simultaneously. You finish one field, go to the other field. So when you are finishing one field or scanning one field, basically it means that you are moving from scan line 1 to scan line 3 to scan line 5 and so on, and finish that field, come back to the next field, start from scan line 0, 2, 4, 6 and 1. So it's alternately meshed, two interlaced scan lines are interwoven. This is the even field, let us say, that is the odd field, and they are interlaced in terms of horizontal scan line. You scan by 1, 3, 5, 7 and so on, and in the odd field and even field you take 0, 2, 4, 6, 8 and so on. So they are just interlaced, and we will see a picture of what they mean by this interlacing or interwoven of these corresponding fields. And you will see that we need to have now two types of retrace for each field, because the same retracing will not work for both the fields. Yeah, this is a picture which probably shows the interlacing action. That's a small yellow gun on the left hand side of the screen, where the beam will be coming out of that gun and scanning the horizontal scan lines. The interlacing scan lines on a raster scan display are shown here. First, all the points on the even numbered, which are marked as 0, 2, then 4 and so on, are solid. Scan lines are displayed and they will be scanned, and then the odd number, all points along the odd numbered or dashed lines are displayed. The dashed discontinuous lines are the odd numbered lines 1, 3, 5, 7 and so on. So that's the way it will finish. So you will finish the odd and the even, or start with the even and then finish the odd, and of course at the end you are at the bottom right of the screen. That's what it showed. But the mechanism of retrace is not straightforward. It is conceptually similar to what we talked about retrace, but since there are two fields now, we will see what this mean. Okay. Let us take a schematic diagram of a 7 line, just to simplify the case, because if I had taken a 512 lines, I couldn't have accommodated on a screen, although the screen which you are seeing will consist of 640 by 480 lines or 512 or 1024, depending upon a TV monitor or a high resolution CRT monitor, but I can't show so many lines. So I have taken a very simple example to show how the scan is done in every alternate field. So we are taking a schematic of a 7 line interlaced scan line pattern, and let us see what happens. Okay, so let's take this as the screen. All that appears field, but let us say it is completely pitch dark, black, nothing is there, and we start scanning. We start scanning with the line at the top right. If you can see, there is a half scan line, horizontal scan line, starting from the top middle of the screen and going to the right. I'll redraw it again. Here you see, okay, you see it's coming from the top middle here of the screen and scanning and finishing at the top right somewhere. Okay, so that's a half scan line being done. We'll see why it is like that and why it starts with half. Once we finish the entire cycle of both the fields, this will be apparently very, very clear. Go to the top right, you need a retrace back. Okay, so now the retrace will come. That's the retrace line. That's the horizontal retrace line for a particular field. So this could be an odd field or even field, doesn't matter. You can take it to be anything. Let us take this to be an even field. So it's something like a 0th scan line, scanned half of it, half of the screen, and then full horizontal retrace, which is given by this dashed discontinuous line with somewhat of a approximately about a gray or a brown color is what you see, and this goes on. So the next horizontal scan line will be full, starting from the finishing point of the retrace, horizontal retrace, to the extreme right. So this the arrow marks are also shown as the how the, remember this is going at a very fast rate, but I am putting it slowly so that you can feel what goes on. So you keep doing this horizontal scan, now it is inclined. Both the vertical retrace and the horizontal scan lines are purposefully made so that the circuit design for the video controller in terms of implementing the horizontal deflection voltages and vertical deflection voltages are made very easy. So sometimes in most occasions you have the horizontal scan also inclined a little bit to the right, almost in a similar slope like the horizontal retrace. So this goes on. So this gone, again a horizontal retrace has come, again a horizontal scan for a particular field. These blue lines correspond to horizontal scan lines for only one particular field. So this could be some odd number or even number of lines. Okay, so we are skipping one line. You can see that the gap is very large. That means the other alternate scan lines for the other field is untouched in this case, and that will come once this field is over. Again a retrace back again. Now let us assume that we have drawn about 3.5 lines. That typically makes it up, because we talked about 7 lines of display, 7 by 2 in each field, that makes you 3.5 lines. So we have drawn 3.5 lines. Typically we have finished one field. We have finished drawing one field on the screen and we have reached the bottom right. Now what do you need? You need typically a a retrace back, a vertical retrace back, and it is almost diagonal. You can see I am going to draw now on the screen. It will come up the vertical retrace, which will take the beam now, which is on the bottom right of your screen, and will take it back to somewhere on the top left. Okay, so let's see how this beam traversal path for the vertical retrace. Yeah, that's the one. I hope it's visible, and the arrow indicator shows that the beam is now taken back by a vertical retrace diagonally across. This is very easy. This is, we have seen this diagram almost earlier, except this field part is basically new. Now remember, it has stopped at a particular location, ready to draw a horizontal scan line, the first of the other alternate field. Remember, 3.5 lines of field A or field 1, which consists of, say, even line 0, 2, 4, 6 are over. So I'm talking about the alternate field to start, and it will start in this form. I've used a different color with an arrow mark to show you the horizontal scan line of the first horizontal scan line of the second field, or the field B, or the even field. If you have finished the even field, if you have started, this is the odd field. If you have finished the odd field, this is the first line of the even field. Whatever way, you can start with any numbering. I have don't worry about the numbering for this at this point. So again, the pattern is same. The pattern is same now as we did in the other field. So you need a horizontal retrace back. The picture is starting to get a little clogged up, but the lines have good spacing. I hope you'll be able to follow. The same, I use the same color for the horizontal retrace for the other field. Again, horizontal retrace. The horizontal scan for field B. Horizontal retrace back. Horizontal scan again, and finally a horizontal scan again. Now we have reached the bottom left of the screen. If you see the pattern, the picture is not complete. Before completing it, I want to show you something. I have 3.5 lines of blue for field A, and just 3 reddish or pinkish lines for pink colored lines for field B. Okay, so the two fields, one of it is fully complete. Field A has 3.5 lines, field B has 3 lines. Where is the half line coming? It's coming here. So at the end of field B, the beam will now be at the bottom center of the screen. It's very nice because we started in the top center. We started at the top center of the iteration here, and after 2 fields have been scanned, it's very nice and ideal to see that the beam is now at the bottom center of the screen. And if you see again the picture very nicely, if the picture is probably scanned and opened up for the entire screen, we will see that there are 3.5 lines drawn for this picture is okay. You should be able to visualize here that there are 3.5 lines for blue lines for the field A, and 3.5 pink colored lines for the field B. So totally I have drawn 7 lines. We talked about, lead the heading of this slide, schematic of a 7-line interlaced scan line pattern. So 7 lines have been drawn, but there is one, because we need retrace, so there must be a vertical retrace. The final vertical retrace is drawn by this reddish line here, which brings back the beam to the top center of the screen where we started. So we have finished the complete cycle of a frame, single frame, or 2 fields, 2 interlaced fields. Adjacent fields, interlaced is the, or interwoven is the particular word used. Remember, I didn't ever say that the fields are consecutive, that you finish field A first and then field B1. No, they are all interlaced. So you finish field A with odd lines, let us say, or even, whatever the case may be, and then the next field is interwoven, is also covered with corresponding the other odd or even scan lines. Okay, so let me retrace back the entire sequence so that you follow what's going on the screen. Correct? We start from the top center of the screen and go through horizontal and horizontal retrace and cover field A. You can see the arrows marked for the blue lines and the retrace back. So 3.5 lines over, then we come across to a vertical retrace. Field B will start, scan, retrace, scan, retrace, scan, retrace, scan, 3.5 lines, both fields over, finally a vertical retrace. So I hope this concept is very clear as to how this is done. This is done for 7 lines. Now you can extrapolate it and think about 525 lines or 512 lines as the case may be. Put the numbering for you to understand. The numbering of the lines are also now there. As you can see, the blue lines should be numbered as 0, 2, 4, and 6, and the odd numbers are marked as 1, 3, 5, and 7. Okay, so there are 3.5 lines, and the statement also says what I have been describing so far. The odd field begins with 1, The horizontal lit trace is shown in dashed. The odd field vertical lit trace starts at the bottom center of the screen, and the even field vertical lit trace starts at the bottom right. The even field vertical lit trace is the one which ends with the blue line at the bottom right. That is a diagonal vertical lit trace. For the even field and for the odd field, it's a simple vertical lit trace. So this entire cycle can go on. Okay. Continuing with horizontal lit trace, as the electron beam reaches the right edge of the screen, it is made invisible and rapidly returns to the left edge. Now the word rapidly is very interesting here. It means that the time taken for the beam to move from left to right when it is scanning is much more than the retrace. Retrace, the beam is switched off. Okay. Yes, that's what is the value numerically. The time taken for a horizontal lit trace is typically about 17% allotted for a scan line. That means if you take about, say, 100 units, not 100 milliseconds or even less, 100 microseconds for a scan line, actually the value is much less. Horizontal 100 millisecond for a horizontal scan line to go from left to right, the retrace will take 17 milliseconds, okay, more. Or if the total inclusive of the horizontal scan cum retrace is 100 milliseconds, you can start to visualize it will about 83 milliseconds here and about 17 milliseconds here, or 85 and 15 of that order is what you will get. After every odd scan conversion is complete, the beam is at the bottom center of the screen, that we have seen with the previous diagram. And after even field scan conversion is complete, the beam is at the bottom right of the screen. So just these are again reiterating the points which we have just discussed with the animation in the previous slide. We know what the bottom center, top center, and bottom right and bottom center as well of the screen, and on what field, alternate fields it will happen. The odd and even words could be interchanged. Odd field vertical retrace returns the beam which is switched off to the top center of the screen. Okay, and the even field vertical lit trace returns it to the upper left corner of the screen. So the vertical lit traces are of two different types. Unlike the common model which we had picked up earlier, now with two fields which are interwoven, the vertical lit traces are of two different types. One for an odd field, one for an even field. One returns it to the top center, another returns it to the upper left corner of the screen. Okay, so that we have seen with the animation in the previous slide. Okay, two fields have to be presented alternately for each frame. So we are, if we are presenting 30 frames per second, then we are talking of 60 fields per second, and if we present 60 frames per second, we are almost talking of 120 fields per second. Okay, so that's typical. In NTSC, I did say some time back in a few slides, this number should not be astonishing for you, that it has 525 lines, but 483 lines are visible, and that will come easily. If you do a little bit of calculations, we will come to know why purposefully 483 lines out of 525 are made visible, not all of these. It's something to do with the vertical and horizontal lit trace times. Yeah, this is because the vertical lit trace after each field, remember there are two fields, so the vertical lit trace after each field requires a time equivalent of 21 scan lines. So 21 scan lines are required for a vertical lit trace. For each field there are two fields. If there are two fields, we are losing time for about 42 scan lines, 21 multiplied by 2. So we are talking of each field, we have the time to display 525 lines divided by 2 for each field, so which is 262.5 minus 21, which gives 241.5 lines per field, and 241.5 lines per field multiplied by 2 gives you a simple figure which you have at the top middle of the screen, the 483 lines. This 483 comes out of this multiplied by 2, 241.5 multiplied by 2. You can easily get it here and actually subtract 42 from 525, you will also get 483. So that's another way by which you can do the calculation. So purposefully, to account for the time for the vertical lit trace, not all the 525 lines are made visible. 483 lines or 241.5 line per field is made visible. So both field together, so we have 483 lines, we just talked about that right now. Either you can multiply this or you can subtract from 525 a number 42 and you should be able to get 483. Okay, this is the reason why 42 invisible lines exist in an NTSC type of display. Actually, it's supposed to have 525. Physically, 483 lines are visible. Physically, there are 483, but it is visualized as if there are 525 lines, and the time spent in the vertical retrace is equivalent to as if you are trying to scan the rest 42 lines. That's the way you should try to visualize. So, as if the system doesn't, you can visualize as if the system doesn't have a vertical retrace or loses no time for a vertical retrace. Okay, it just tries to scan all the 525 lines. That's the way to visualize it. But basically, out of those 525, 42 are not made visible because that time is used for the vertical retrace. Do some more of calculations, a little bit of geometry, algebra, whatever you say. Let the time available for each scan line be t, and you have, now we talk of 525 lines. Remember, although 483 lines are visible, we consider 525 because that it takes into account the time for what? Vertical retrace. Okay, so we are talking about 525 lines, which is 483 visible lines and 42 invisible lines, which account for the time for the vertical retrace of both the fields. So we are presenting 525 lines, actually 483, 525 lines multiplied by 30 frames per second, and t is the time to scan each line. 525 lines 30 times per second. So that's the calculation which gives you 1 second. This gives rise to a value which tells you that the value of t is as low as, forget millisecond, it is 63.5 microsecond. That's the time for a scan line, which is 63.5 microseconds. Okay, that's as low as about that. And this includes the vertical retrace time. Okay. That's the time. So typically what this means is probably you will have 17% less time of t for each scan line, because we are talking of this t, actually you are visiting 483, and the 42 lines time is inbuilt into the t. So this includes the vertical retrace time. When we consider the horizontal retrace time, that also has to be considered, because that is about 17%. That's about 17% of the time for a scan line is spent for a horizontal retrace. So when we consider the horizontal retrace time, the actual time to display all pixels in a scan line, that is the time in bracket which you can see on the screen here, the time to scan from left to right only. Forget about the retrace time, that is a part of 63.5 microsecond. So 53 microseconds, or 0.83 multiplied by 63.5 will approximately give you 53. I have rounded off the value. 53 microseconds is spent on scanning from left to right, and about 10 seconds is left over for the horizontal retrace of the beam to come back from right to left. So that's the typical calculation which you have for a scan line. 53 microseconds spent for just scanning. The rest, about 10 seconds, goes for retracing back. Okay. And considering a 4:3 aspect ratio for an NTSC display, you can take the calculations for PAL, but since we started the NTSC, let me stick to that. The books we have referred talked about NTSC more. Considering a 4:3 aspect ratio, the number of pixels per scan line is 4/3 of 483. That means if you have 483 scan lines, each scan line will have about 30% more than the number of scan line. The number of pixels in a scan line will be more. That means typically you have more vertical columns in the array than the horizontal rows. Typically a screen in a picture TV or video or a monitor, you will see that the aspect ratio is such that the horizontal width is probably more than the vertical height. That's because the number of pixels on each scan line is more than the number of, actually the number of rows. So if you have n rows, you have more than n in terms of the number of pixels. So if you're talking of a matrix of array for a refresh screen, you have a size of m cross n. So if this S is n, that is m, and that is n number of rows, the number of columns which m is typically more. So its aspect ratio is 4 times 3 here. So the number of pixels per scan line will be 4 multiplied by 483 by 3, the number is about 644. So the screen shows that the number of pixels per scan line is 644. So that's more than the number of horizontal scan lines. Well, if that is so, and you have 53 microseconds to scan a horizontal line from left to right, and there are 644 pixels per scan line, you can now imagine the time crunch you have to display a pixel in terms of Let's read this sentence. The time available for the beam to access and display a pixel is 53 microseconds, which is t prime, the value here, divided by 644. Okay, so you get a value of about 82.3 nanoseconds, 10 to the power minus 9. That's the time allocated for the beam to access a pixel and move over to the next one, and within this time the beam must switch on and switch off if it is so required. So you can imagine the amount of bandwidth which is demanding for a typical CRT monitor or for a video in terms of trying to access a pixel and display it. That's the rate at which the beam must move and also work. Okay, you can do the same calculations for different values of frame rate and different display resolutions. These are typical examples of frame rates and display resolutions, and the first row says that if you have 30 frame rate and a 512 cross 512 resolution, you can work in the same way in which I have shown the calculation in the previous slide, and it works out to 105 nanoseconds. Remember, the NTSC we considered 512 cross 644 resolution, 30 frames per second. Frame rate of 30 gave us 82.3 nanosecond. So 512 by 512 multiplied by 30 will give you a little bit more. It gives you 105 nanosecond. It's same for a 500 cross 625 resolution display with a frame rate of about 25, gives you 105 nanoseconds. Now let us start to go for higher frame rates and higher resolution CRT monitors. The last two rows, amazing. 60 frames per second, 1000 cross 1000 display resolution. You just have 26 nanoseconds to access a particular pixel. 60 frames per second, 1024 by 1024 display resolution, you just have about 24 nanoseconds access time for accessing a pixel. You have 24 nanoseconds to get the beam on, display it and turn it off. If that is the rate at which the information must pass on from where? We are talking the information whether the beam has to be switched on or off between two adjacent pixels from the frame buffer. From the frame buffer through the video controller, registers and access registers, data registers, up to the deflection voltages in terms of electronic gun strength, 24 nanoseconds time on off, turn on off, and the on time is even half of that. We talked about n by 2. So the beam on time will be even less than that. So we are talking about a few tens of megahertz already in terms of almost 100 megahertz, close to about few tens to 100 megahertz type of bandwidth frequency rate. You can calculate that easily by 1 by 24 or 1 by 12 nanoseconds. So that is how the display will go. A little bit about coming back to the frame buffer. We talked about a lot of video basics and timing, bandwidth, and we talked about architecture earlier. We talked about memory requirement also. We move on to the capacity of the monitor system in terms of grayscales and color, and how does it depend on the value of n, the bit plane size. N could be 1, black and white. We talked about this earlier. More larger the n, more the feasibility or you may have, the programmer may have in fact, in terms of controlling the number of grayscales or colors. So the choice of the number of grayscales and colors depend on the value of n, that's the bit plane size n. If n is equal to 1, we talked about this earlier, I repeat again, 2 colors, n equal to 3, you have 8 grayscales or colors, n equal to 8, you can have 2 to the power 8 or 256 gray shades or colors, n equal to 24, you can have 16 million colors. Okay. For color displays raster scan, we need 3 separate color guns to operate simultaneously. So far we have been talking of one electronic gun, the bit value passed on to that by a register, a digital to analog converter will convert that bit value to an analog voltage, not for the deflection plates but for the strength of the electron gun, which must control the strength or intensity of the, in fact the strength of the beam, which will in turn control the intensity of the pixel or that color spot which will grow on the screen. So you can't do that with color displays with just single gun. You need 3 separate guns for each 3 separate colors. Typically RGB is used, and so we talk of each bit or a byte plane having a separate gun, or each byte plane being driven by a color gun. Okay, let's take a very simple example. Let's take a very simple example of a single bit plane black and white frame buffer raster CRT graphics device. Okay, so on the left hand side we have an array of pixels, a frame buffer, you have a 1 bit register which will take out, this is all controlled by the video controller. Okay, so you don't have to worry, the programmers don't have to worry about this. It typically you just access the frame buffer. The rest of it is automatically done by the video controller, which is part of your graphics adapter card, which sits between your system bus and the monitor. Okay, it has an output, analog output, but takes in digital values from the frame buffer. It will have a value 0 or 1, which will be converted by the DAC or digital to analog converted into a voltage 0 or some high voltage. Well, you have an electronic gun which will fire onto the corresponding same point onto the CRT raster on the screen. So that's a very simple example of what is the mechanism which happens for a CRT graphics device in terms of a single bit plane. Let's now stretch that single bit plane to n bit planes. If we have n bit planes, we can visualize this n on the left hand side of the screen as n layers of single bit planes, correct? If you take a single n bit value, there are about n bits for a single byte or a word, as you can see. So you can visualize, instead of having a single bit, you have n bits. So some n layers of bit planes is our frame buffer. So there are n such layers, although 3 layers are shown, but typically there are n layers. And what at any particular time when you want to display a pixel, earlier we are taking a single bit value out, now simultaneously all the bits for that corresponding byte or word for a intensity of a screen is taken out and loaded onto an n bit register. We have an n bit register at the center of the screen, which you can see. So that n bit register takes values from n bit locations or from the n bit frame buffer or n bit plane. Various terminologies are used, and the register is very fast. It in fact immediately sends out the digital value to what I will call as now a 2 to the power n digital to analog converter. 2 to the power n digital to analog converter, and 2 to the power n was the case where in the previous case n was only 1, so 2 to the power n is 2. So we had only 0 or 1 output, 2 levels. Now we have 2 to the power n different outputs, 0 to 2 to the power n minus 1 different levels. A digital to analog converter, those with electronic circuit backgrounds or even electronic engineers background will easily follow this, that it takes an n bit value and you will have 0 to 2 to the power n minus 1 levels, or totally 2 to the power n levels. So the electronic gun takes in analog voltage at 2 to the power n different levels. So the output of the electron gun, which is the electron beam, will have 2 to the power n different type of strengths from 0 to 2 to the power n levels to the maximum. So okay, so that can be controlled by the analog voltage, which is output of the DAC. The DAC input is the n bit register. So n bit register takes the input from the frame buffer. So in fact the word comes out from the frame buffer to the register to the DAC. Analog voltage generated, driven to the electronic gun. The electronic gun gives out an electron beam with intensity which is proportional to the analog voltage given out by the DAC, and the CRT raster now has a beam which is will be hit, the spot at the CRT raster will be hit by the beam of a corresponding strength as given by the bit value in the frame buffer, and it will glow with that certain intensity. So this is an n bit plane gray plane frame buffer. The next question comes is, well, n bit planes, when you are talking, you have either an n bit gray level or n bit color. You have an n bit gray level or n bit color. When we have an n bit grayscale in terms of monochrome gray shades from dark to white and all gray shades black and white in between, this model is fine, but we can still move towards colored model with n bits. It gives an option, and when you talk of a color screen, you need to have 3 guns, not the one particular gun I just shown before in the previous 2 examples. You need to have 3 guns for 3 different colors. An n bit plane, n could be 8 or even more, and you will need to have separate registers for each electron gun intensity, n 2 to the power n several DACs, separate registers, separate DACs for each color, separate gun for each color. Frame is same, CRT buffer same. So we'll move to the next lecture when we talk about the n bit plane but colored frame buffer, not gray level buffer. Okay, so we'll meet next time. Thank you very much.